Okay, I'm back. So again, here's our data, 3, 1, 5, 6, 7, 8. Find the line of best fit for this data. So what we're looking for is the ordered pair m comma b such that the sum of the squares of the residuals is minimum. Sum of the squares of the residuals is minimum. Okay, let's do it. It's pretty complicated. So here we have 3, 5, 7 and 1, 6, 8. Well, first of all, what is y hat for this data? Well, y hat is just mx plus b, so if I plug 3 into the y hat equation, I just get 3m plus b. Here I get 5m plus b, and here I get 7m plus b. Try to stay a couple steps ahead of me. Okay, now we calculate the residual for each one of these numbers. Well, the residual is y minus y hat. So it's, for this first one, it's going to be 1 minus all this. So 1 minus 3m minus b. Here it's going to be y minus y hat. So 6 minus 5m minus b. And here it is going to be 8 minus 7m minus b. Okay, and now we have to square these numbers. Well, it actually helps to have like a little formula handy for the square of a trinomial. If you multiply this trinomial, well, that's just a plus b plus c. So if you just do it out, you just get like a squared, and then there's also, okay, I'll just do it, plus ab plus ac plus another ab plus a b squared plus a bc plus an ac plus a, not ac, an ac plus a bc plus a c squared. In other words, when you multiply two trinomials, you get a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc. So that's kind of a nice little formula with 6 terms. All right, so we do it. We're going to get 1, so that first number squared, plus 9m squared, plus b squared, and then plus twice the product of these two, so minus 6m, then plus the product of these two, so it's going to be plus 6mb, I guess. And then, no wait, something went wrong. Minus 6, and let's do AC for following the pattern. So minus 2b, and then plus 6mb. Okay, and just like keep going. Yeah. Yeah, I am making a video. What do you need? Oh, him. Okay. I got distracted.
Sorry.
What am I doing?
You're calculating residual square.
Oh, yes.
I think I did that right? No, 14. I think that is correct. Okay, and if we add these all up, 58 and 25. No, I'm serious.
82.
No, I don't think so. 83. That number looks familiar.
It's okay. I only took 2 guesses compared to his 3.
I can do calculus on basic math.
I can't do either.
So it's not plus.
Plus. Okay, so hopefully that is correct. If it's wrong, I'm going to cry. I did do this at some point a long time ago, so I really hope, but I can't find my answer key, so I'm just doing it now. I think that is the right answer. All right, this does not actually help me that much at the moment. It gives me, well, okay, so we just did it, right? We took our data points, and this is, oh, by the way, this has a name, this thing that we're doing. It is called linear regression by brute force. This is what Forster calls it. In other words, you just crank this out with like a pencil and paper. We calculate the predicted y value, we calculate the residual, we square the residuals, and then we add them. All right, so what I have here is some just terrible expression, which is actually 2 variables, and I'm looking for the ordered pair such that this expression is smallest. All right, this sounds really hard. This is like some kind of multivariable calculus problem or something like that. There are 2 variables. They can each differ, and I want to find when this is as small as possible. Well, here we have a strategy here, and the strategy is let's find the minimum m for a given b and find the minimum b for a given m. Okay, which should we do first? Well, first let's find the minimum m for a given b. Okay, so what we're going to do is we fix b and minimize m. Well, if our goal is to fix b and minimize m, we're going to let b be a constant. So if b is a constant, let's rewrite this expression so that it is quadratic in m. Okay, well, what we have then is 83m squared plus the coefficient of m is 30b minus 178. And then there's a bunch of other crap, right? There is 3b squared minus 30b plus 101, but that's all just constant. We treat b as a constant and we write it as a quadratic in terms of m. All right, well, what is the minimum m given this expression? Well, this is just a quadratic. I know how to do this. Any quadratic will have its minimum. This is a parabola with leading coefficient positive, so when at negative b over 2a. So m will be, so the magical number m that we want is the one where the opposite of this over 2 that. Okay, that wasn't so hard. Now, let's fix m and minimize b. Okay, now we take the same expression in 2 variables and we treat m as a constant and we treat b as our variable. So then I get 3b squared, and then the coefficient of b is 30m minus 30b. I think that's right. Yeah, and then plus a whole bunch of stuff which ends up just not mattering, which I think you're getting the idea that, right, the y value kind of, or the value of sort of c doesn't matter for the optimization problem. Okay, when is this expression, for what b is this expression smallest? Okay, well, that will be smallest when negative that over 2 that. Okay, so transforming this slightly, let's see. This can be, I guess I can divide through by 2. So I get m equals negative 15b plus half of 178 is something. 89? Yeah, hope so. And that's over 83. So I can actually write this as 83m plus 15b equals 89. Those numbers really do not look familiar. I'm gonna cry if this is wrong. All right. Yeah, anyway, okay. And over here, we can also clean this up a little bit. We can divide by 2. I get negative 15m, and then that's plus 30, so plus 15 over, oh, actually I could have divided this through even easier. This is just negative 5m plus 5. So here I get the equation 5m, that's right. Okay, hope so. Hope so. Hope so. Okay, so this is 5m plus b equals 5. Yeah. Okay, so the question is, I think this is the exact example that Forster gives. Let's take a moment and check. And if it's wrong, I'll throw out this video and I'll cry. Yeah, something went wrong. Plus b 83m plus 15b equals 89 and 5m plus b equals, oh yeah, everything is good, yes! I'm so freaking happy. Okay, so now we have to think for a minute. Here comes the thinking. The thinking is, if I want to know when this big expression is as small as possible, I need to find the ordered pair which makes it as small as possible. Well, what is this line really? This line is a line which produces the minimum m for a given b. So you can sort of think of there as being kind of like a graph. So this is b and this is m. This first line, this line 83m plus 15b equals 89, whatever you want to say about that line, what that line predicts is the minimum m for a given b. In other words, you give me a b, and then this function produces the minimum m value. As b varies, there is a different m, which makes this expression as small as possible. So it's going to be some kind of graph or something like that, right? As b changes, every point on this line is the minimum m value for that particular b. This other line, this is where we fixed m and we tried to minimize b. So what this is a function which, for a given m, gives you the best b. So if this line gives you the best m for a given b, and this line gives you the best b for a given m, wherever these two lines cross, that has to be the magical ordered pair which minimizes the quadratic. In fact, maybe even a better way to think about it is, if this first line over here, for any given b, this gives you the best m. So the absolute ordered pair, which is best, must lie somewhere on this line. And over here, the second one that we did, we fixed m and minimized b. So now what this line tells you is, for a particular m, so we're plotting along the y-axis now, for any particular m, this line gives you the best b. So the best overall ordered pair must lie somewhere on this line. And so the overall ordered pair has to lie on the intersection of the two lines. And so all we have to do now is to solve this system of equations, and we've solved this kind of two-variable minimization problem. Okay, let's do it just like as fast as possible by just like whatever random techniques. I will multiply, I guess, by 15. It seems like a good idea. If I multiply by 15, I get 75m plus 15b equals 75. So this is 8m equals 14. So m is 14/8, which is 7/4. And if m is 7/4, then b is 5 minus 5 times 7/4. And whatever that is. So that's like 20 minus 35/4, negative 15/4. Okay, therefore all this work predicts that the y-hat model is 7/4 x minus 15/4. That this is the absolute line of best fit for this data. And we can actually now check this. So you should take out your calculator. See if this works. You should take out your calculator. No, how do I do this? I don't think this camera rotates in that direction. You wouldn't believe the stupid thing I'm doing right now. This video is terrible. Let's just do that. Okay. So, no, that's not going to work. Maybe I'll just go handheld. Maybe I'll just do this later. All right. So yeah, you can type this into your calculator, although I don't feel like doing it right now. But if you, or maybe we'll just do this. Yeah, okay, perfect. So let's go into y equals and type this equation, 7/4 x minus 15/4. Enter. And then we can go into list and, stat, edit, and let's clear all these lists. Clear all lists. Okay, and we will put into L1 3, 5, 7, and we will put into L2 1, 6, 8. And then we can do a stat plot on, let's plot L1 versus L2. And if we quit and we do a zoom 9, we can see those are our 3 points and our line of best fit, 7/4 x minus 15/4. It looks pretty good. Okay, cool. That's how you do this. You're going to read Forster and you're going to do like 2 of these or so. All right, bye functions class. See you after spring break.